The last topic we'll talk about are bond energies, chemical reactions involving breaking bonds and reactant molecules and forming new bonds to create the products. The enthalpy of a reaction, that's what delta H stands for, is enthalpy, can be estimated by comparing the cost of breaking old bonds to the income from making new bonds. This amount of energy needed to break 1 mole of a bond is called its bond energy. Typically, they are reported in the gaseous state and homolytically, just simply saying each atom gets half of the bonding pairs of electrons. How much energy is needed to break 1 mole of a compound's bond is called its bond energy. The actual bond energy depends on the surrounding atoms and other factors, but we often use what are called average bond energies to just simply estimate the enthalpy of a reaction. These enthalpy of reaction really is just given to us in a chart, and here's one now. It's on slide 71. This is a chart then taken from our chemistry book, table 9.3, and it's just take a closer look. It's telling us how much energy each type of bond is required to just break them in half. If I wanted to break an HH bond, I'd have to put in 436 kilojoules for every 1 mole of hydrogen. If I wanted to break a double bond to carbon, 611 kilojoules of energy is required. So it's just giving us an average amount of energy needed to break a bond. So these average bond energies are reported to us in a table. We simply look them up. Bond breaking is endothermic. Bond making is exothermic. Breaking bonds requires energy. Making bonds releases energy. Important note, if I'm breaking bonds, the sign on delta H is positive. If I'm forming new bonds, the sign on delta H will be negative. The heat of the reaction is the sum of all the bonds broken plus the sum of all the bonds formed. Forming bonds is exothermic. Bond breaking is endothermic. Keep in mind when we read the charts, we'll have to make sure if bonds are breaking on the reactant side, those are reported as positive numbers. Bonds are forming on the product side, those will be reported as negative numbers. Let's take a model problem. Oh, we'll do that in a minute. We'll talk about trends in the bond energies. This is a slide that's saying the more electrons that 2 atoms share, the stronger the covalent bond will be. Notice that a triple bond carbon requires much more energy to break than a double bond carbon compared to even a single bond carbon. The more bonds between 2 atoms, the more energy is required to break that. In general, the shorter the covalent bond, the stronger the bond. Triple bonds are much stronger than double, which is much stronger than single. And remember that resonance structure, the hybrid, would lie somewhere between a single and a double bond. So the amount of energy needed to break a resonance structure is a little different as well. In general, the shorter the bond, the stronger the bond. You can see comparatively a single bond bromine to fluorine, 237, a little less for bromine to chlorine, and a little less yet for bromine to bromine. So they get weaker as you go down a column. As you go down, remember that atoms are getting larger. As you go across the period, the bonds get stronger. Remember that atoms get smaller as you go across a row on the periodic table. Now let's take a peek at an actual problem. And I wrote on this, I apologize. I'm going to read through my writing. We have a compound CH4 plus Cl2 giving CH3Cl and HCl. And what's nice is that they've actually drawn for us the structural. On the left side, I can see that a carbon to hydrogen bond had to be broken. Carbon to hydrogen bond is 414. That's where they're finding this value. Bonds broken end up to be endothermic, positive value. I also had to break a chlorine to chlorine single bond. And again, using our chart, chlorine to chlorine's on the bottom of the second middle column there, 243 kilojoules. The sum of all the bonds breaking is 657. Over on the product side, I had to create a carbon-chlorine bond. It was a carbon to hydrogen. On the product side now, it's carbon to chlorine. Carbon to chlorine, 339. Notice the negative sign is being placed there because now the bonds are making, and that's exothermic, negative value. We made an HCl. HCl, again, I just look up, hydrogen to chlorine is 431. Report that as negative because it is forming a bond. Those are exothermic. The total energy then in an exothermic value, 770 for the product side. The sum of all the bonds broken, 657, notice bonds broken, endothermic value for the reactants, plus the exothermic sum for forming new bonds gives us a net heat of reaction of negative 113 kilojoules. This is an exothermic process overall. Energy was released during the course of this reaction. Estimating the enthalpy change of a reaction from bond energies. This is just a picture of what we went through. Methane plus chlorine. To break the bonds required energy. We input energy, so it went up positive value. So now we've broken a bond. I see hydrogen has been broken and the two chlorines have been broken apart. We then make bonds. We form a carbon to chlorine and a hydrogen to chlorine. That is an exothermic process. The overall change from the amount of energy input and the amount of energy let go ended up to be a net negative. Overall process was exothermic. In this practice problem, we can see that hydrogen would have to be broke. A double bond oxygen would need to be broken. We'd have to form two OH single bonds, two of those, and we'd have to form an OO single bond, one of those. We're breaking an HH and we're breaking an OO, O double bond O. Breaking bonds is endothermic, forming new bonds is exothermic. Take a moment and try this sample problem and turn the video on when ready.